Welcome, everyone. Today, we're diving deep into one of the most revolutionary technologies of our time, deep learning. We'll explore how machines are learning to think, see, and understand the world around us in ways that were once thought impossible. From recognizing faces in photos to powering chatbots like ChatGPT, deep learning is transforming every aspect of our digital lives. So buckle up as we journey from the human brain to machine intelligence. So, what exactly is deep learning? Think of it as teaching computers to learn like a child does, through experience and repetition. Deep learning is a subset of machine learning that uses artificial neural networks with multiple layers to model and understand complex patterns in data. Let's break this down with four key characteristics. First, it's brain-inspired. These networks mimic how neurons work in our own brains, with interconnected nodes passing signals to each other. Second, it has a layered structure. Multiple layers of these artificial neurons work together, each layer learning increasingly complex features. The first hidden layer might detect simple edges in an image, while deeper layers might recognize shapes, then objects, and finally complex scenes. Third, it excels at pattern recognition. It can identify incredibly complex patterns in data that would be impossible for traditional programming to handle. And finally, it's self-learning. The more data you feed it, the better it gets. It literally improves its performance through experience, just like we do. Now let's look at the architecture of a neural network. This is where the magic happens. What you're seeing here is a simplified view of how these networks are structured. On the far left, we have the input layer. This is where raw data enters the network. Think of it as the eyes and ears of our artificial brain. In the middle, we have hidden layers, and this is where deep learning gets its name. These hidden layers are where the real learning happens. Each layer transforms the data, extracting increasingly sophisticated features. The first hidden layer might detect simple edges in an image, while deeper layers might recognize shapes, then objects, and finally complex scenes. Finally, on the right, we have the output layer. This produces the final result, whether that's identifying what's in an image, predicting a stock price, or generating text. Notice how every neuron connects to neurons in the next layer? These connections have weights that determine how much influence each input has. During training, the network adjusts these weights millions of times to improve its accuracy. It's like fine-tuning a massive, complex instrument. Let's follow the journey of data through a deep learning system. This process happens millions of times during training, and it's absolutely fascinating. It starts with raw data. This could be images, text, audio, or any type of information. The data flows into the network like water flowing through a series of filters. Next comes feature extraction. Each layer of the network automatically learns to extract meaningful features from the data. This is revolutionary because traditionally engineers had to manually program what features to look for. Now, the network figures this out by itself. Then we have pattern learning. The network combines these features to understand complex relationships and patterns in the data. It's learning rules and associations that might not be obvious even to human experts. And finally, we get a prediction. The network outputs its best guess based on everything it has learned. The mathematical formula you see here represents this process. Don't worry about the complex notation. What's important is that data flows through multiple layers, with each layer applying mathematical transformations using weights and activation functions. It's like a sophisticated assembly line for information processing. Let's dive into the key components that make deep learning networks tick. Understanding these building blocks will help you grasp how these systems actually learn. First, weights and biases. These are the network's memory. Weights determine how strongly one neuron influences another, while biases help the network make better decisions. During training, these parameters are constantly adjusted. It's like tuning thousands of dials to get the perfect sound from a radio. Next, activation functions. These add the crucial element of non-linearity. Without them, our network would just be a fancy linear equation. Activation functions like ReLU, sigmoid, or tan help the network learn complex, curved relationships in data. Think of them as decision gates that determine when a neuron should fire. Third, the loss function. This is the network's report card. It measures how wrong the network's predictions are compared to the correct answers. Popular loss functions include mean squared error for numerical predictions and cross entropy for classification tasks. Finally, backpropagation. This is the learning algorithm that makes it all possible. When the network makes a mistake, backpropagation traces back through all the layers, figuring out which weights contributed to the error and how to fix them. It's like having a personal trainer that can instantly identify and correct every mistake you make.
Not all neural networks are created equal. Different problems require different architectures, and this is where deep learning really shows its versatility. Let me introduce you to the main types you'll encounter. First up, recurrent neural networks, or RNNs. See how the data flows in a sequence? RNNs have memory. They're perfect for sequential data like text, speech, or stock prices. Each step remembers what came before it, making them ideal for tasks like language translation or speech recognition. It's like having a conversation where you remember what was said earlier. Next, we have convolutional neural networks, or CNNs. These are the champions of computer vision. Those moving filters you see scan across images, detecting features like edges, textures, and shapes. CNNs are why your phone can recognize faces, why self-driving cars can see obstacles, and why medical AI can spot diseases in X-rays. They're inspired by how our visual cortex processes images. Then we have long short-term memory networks, or LSTMs. These are like RNNs with a superpower. See those three gates? They control what information to remember, what to forget, and what to output. LSTMs solved a major problem called the vanishing gradient problem, allowing networks to remember information over very long sequences. They're behind many language processing breakthroughs. Finally, transformers, the newest and most powerful architecture. Those QKV components represent the attention mechanism. The network can focus on different parts of the input simultaneously. Transformers revolutionized AI and are the backbone of ChatGPT, BERT, and most modern language models. They're incredibly parallel and efficient, which is why they've become so dominant in recent years. Now let's see how these networks actually learn. The training process is like teaching a student, but imagine doing it millions of times per second. The process starts with forward propagation. Data enters the network and flows forward through all the layers to produce a prediction. At this point, the network is just making educated guesses based on its current knowledge. Next comes error calculation. We compare the network's prediction with the correct answer using our loss function. This tells us exactly how wrong the network was. Think of it like grading a test. Then the magic happens with backpropagation. The error signal travels backward through the network, layer by layer. Each layer calculates how much it contributed to the overall error. It's like a detective working backwards from a crime scene, figuring out exactly what went wrong and where. Finally, we update the weights and biases based on the backpropagation results to reduce the error. This happens using optimization algorithms like gradient descent. But here's the key. We repeat this process thousands or even millions of times. Each iteration makes the network slightly better. It's like practicing a musical instrument. Each repetition improves performance incrementally. Over time, these tiny improvements compound into remarkable capabilities. During training, we also use techniques like batching or processing multiple examples together and regularization or preventing overfitting to make the learning process more efficient and robust. Let's talk about where deep learning is making a real impact in our world today. The applications are truly mind-blowing. In computer vision, deep learning has revolutionized how machines see. Medical AI can now detect cancer in mammograms more accurately than human radiologists. Autonomous vehicles use computer vision to navigate safely through traffic. Your smartphone camera uses it for portrait mode, and security systems use it for facial recognition. We're even using it to analyze satellite imagery for climate research and urban planning. For natural language processing, deep learning has given us ChatGPT, Google Translate, and voice assistants like Siri and Alexa. These systems can understand context, emotion, and even generate creative content. They're helping break down language barriers and making technology more accessible to everyone. In audio processing, deep learning powers speech recognition, music generation, and noise cancellation in your headphones. Musicians are using AI to create new compositions, and podcasters use it to enhance audio quality automatically. Finally, autonomous systems represent perhaps the most exciting frontier. Self-driving cars are becoming a reality. Robots are learning to perform complex tasks, and AI has mastered games like chess, Go, and even video games at superhuman levels. What's remarkable is that we're just scratching the surface. Every month brings new breakthroughs and applications we never thought possible. As we look to the future, deep learning continues to evolve at an incredible pace, and the possibilities are truly exciting. We're seeing more powerful models emerging constantly. GPT-4 has 100 times more parameters than GPT-3, and researchers are building even larger, more sophisticated architectures. These models are becoming more efficient, more capable, and surprisingly, more creative. The real-world impact is expanding beyond technology into solving humanity's biggest challenges. AI is helping develop new medicines, optimize renewable energy systems, predict and mitigate climate change effects, and even assist in space exploration. We're using it to preserve endangered languages and democratize education worldwide. Perhaps most importantly, we're moving toward human-AI collaboration rather than replacement. AI is becoming a powerful tool that augments human creativity and problem-solving abilities. Artists collaborate with AI to create new forms of art. Scientists use it to accelerate research, and educators use it to personalize learning experiences. Finally, there's a push toward democratization, making AI tools accessible to everyone, not just tech giants. Open-source models, user-friendly platforms, and educational resources are making it possible for anyone to harness the power of deep learning. The future isn't just about smarter AI. It's about AI that makes all of us smarter, more creative, and more capable of solving the challenges that matter most. And that's our journey through the fascinating world of deep learning. From mimicking the human brain to powering the AI revolution, these technologies are reshaping our world in incredible ways. The best part, we're still in the early chapters of the story. Thanks for joining me on this exploration, and remember, the future of AI isn't just about the technology itself, but about how we use it to create a better world for everyone. Don't forget to like this video if you found it helpful, subscribe for more AI content, and let me know in the comments what aspect of deep learning interests you most.